Welcome to Nardar Academy. In this video, we are going to discuss about sampling distributions. Okay, just only the key points we are going to discuss here. So this video includes distributions of chi-square distribution, T distribution and F distribution. Okay, now let's start the video with some preliminaries. Okay, see, the first one is population. Population means the collection of all items under our study. Okay, suppose if you are dealing with the results of class 10 students in a particular state. Okay, so the collection of all class 10 students who have written their exams, that will constitute the population. Okay, that may be in lakhs. Okay, right? So that is a finite population. The population need not be finite, it may be infinite also. So the case which I am referring here is a finite population. So the collection of all students who appeared for class 10 exam in a particular state, right? Then from that population I am drawing a sample. Sample means randomly selected elements from the population. See, I find it difficult to collect the entire data from the population. So for my convenience I am selecting only very few students from the population. It may contains 100 or 200 or 300. The sample size may be different as per my convenience. Okay, so from 1 lakh population I am selecting only 500 students, means that is called a sample. Okay, from a population you can draw different samples. The only thing is it has to be random. Okay, right? So you know now what is a population and what is a sample. Now they have their own measures, no, that is mean, median, mode, right? So many measures are there for both for population and also for the sample, isn't it? That is, the population will have its own mean, median, mode, etc. And similarly the sample will have its own mean. Both need not be the same always. Both may be same at few times and both may be different at all the times. Okay, right? Now the mean, median, mode, that and all, no, the measures are there, no. For the population we call them as parameters. So parameters means it is meant for population. And then the same thing that we calculate for the sample, no, they are called statistic. Okay, and these are the standard notations we are going to use in this video. The population mean is denoted by mu and the sample mean is denoted by x bar, and population variance is sigma square and the sample variance is s square. Okay, so with this introduction let us study about the sampling distributions. Okay, see, if x1, x2, xn are independent and identically distributed random variables, we say that they constitute a random sample from infinite population given by their common distribution. See, here each one is independent. Independent means what? That is, they are not dependent. Independent and identically distributed. That means they all have the same distribution. Okay, these are all random variables. Then they constitute a sample from the infinite population. They are given by their common distribution. Let f of x1, x2, etc. xn be the value of the joint distribution. Then the joint distribution is written as product I equal to 1 to n f of xi. Here the joint PDF is equal to product of the individual PDF, because all these random variables are what? Independent random variables. Okay, each one is an independent random variable. Therefore the joint PDF is equal to product of the marginal PDF. Okay, right. Now if x1, x2, etc. xn constitute a sample, then constitute a random sample, then x bar equal to this one 1 by n into summation xi is called the sample mean, and s square is equal to 1 by n minus 1 into summation xi minus x bar the whole square is called the sample variance. So these are the formulas for finding the sample mean and the sample variance. See, here for sample variance it is 1 by n minus 1, not n. Okay, for sample variance. Okay, that is the difference. Okay, right. Since statistics are random variables, what do you mean by statistics? That is the sample mean variance. Okay, they are random variables. Their values will vary from sample to sample and their distribution are referred as sampling distribution. Here comes the main point. Okay, so we know what is a population and what is a sample. What do you mean by sampling distribution? See, from a given population, I can take one sample and you can draw a different sample, isn't it? In that way so many samples can be drawn, isn't it? So those samples which are drawn from the same population, they will, okay, they will form a distribution, and that distribution is called what? Sampling distribution. Because they will also vary, they need not be the same all the time. So what do we say? The statistic means, what do we mean? That is the measures of the random sample. They are all random variables. Their value will vary from sample to sample. That is, I am taking one sample. For that sample I am calculating its mean and variance. You are taking the second sample, and that second sample will have its own mean and variance, and some other person will choose third sample and it will have a different mean and variance. So all the means put together, x1 bar, x2 bar, x3 bar, etc., that will constitute a distribution. And similarly their variance, s1 square, s2 square, s3 square, they will form another distribution. So these are called what? Sampling distributions. So sampling distributions are nothing but the distribution formed by the statistic of the random samples. Understand? Statistics of the random sample. Now first one is, we are going to see about distribution of mean. Okay, let x1, x2, etc. xn constitute a random sample from an infinite population with mean mu and variance sigma square. So these are the population parameters. Mu is the mean of the population, sigma square is the variance of the population. Then expectation of x bar equal to mu and variance of x bar is equal to sigma square by n. What is this x bar? X bar is the sample mean. Expectation of x bar will be equal to mu. So whatever may be the population, right? If you take infinite population, in that case expectation of the sample mean is equal to population mean, and variance of the sample mean is equal to sigma square by n. What is the sigma square? Sigma square is nothing but population variance, right? And what is this n? N is the size of the sample. Okay, so this is the distribution of mean. Next one, standard error. Standard error is equal to sigma by root n. Next we have two important results. One is law of large numbers, another one is central limit theorem. This law of large number says, for any positive constant c, the probability that x bar will take its value between mu minus c to mu plus c is at least 1 minus sigma square by nc square. When n tends to infinity, this probability approaches 1. That is probability of x bar lying between mu minus c to, what is this x bar? Sample mean, and mu is the population mean, and c is any constant, positive constant. Probability of x bar lying between these two values is at least 1 minus sigma square by n square. No, that limiting value is always what? 1. Next one is central limit theorem. This theorem states, if x1, x2, etc. xn constitute as random sample from an infinite population with mean mu and variance sigma square, then moment generating function is mx of t, then the limiting distribution of x bar minus mu by sigma root n is the standard normal distribution. So what does it say? Is x bar minus mu by sigma by root n is the standard normal distribution when the sample is drawn from an infinite population. Okay, what is this x bar? As usual, sample mean, and mu is population mean, sigma is population standard deviation, and n is the sample size. So this follows standard normal distribution. What do you mean by standard normal distribution? It is the normal distribution with mean equal to 0 and variance equal to 1. That is called standard normal variate, right? Next result, if x bar is the mean of the random sample of size n from a normal population with mean mu and variance sigma square, then the sampling distribution is also a normal distribution with mean mu and variance sigma square by n. So this is what already we have previously seen in distribution of mean. The difference between the previous statement and this statement is, previously I have selected the sample from an infinite population. Okay, infinite population I have taken. In that case, expectation of x bar equal to mu, variance of x bar equal to sigma square by n, whatever may be the sampling distribution. Okay, but this follows like that. But here we are taking a finite population, and that finite population is normal. Only when the finite population is normal, this thing is true. This is not true for any other finite population. Okay, only for finite population with normal distribution, this result holds. Okay, right. Then let us now come to the distribution of mean for finite population. So if an experiment consists of selecting one or more values from a finite set of numbers c1, c2, etc. up to cn, this set is referred as a finite population of size n, isn't it? Because the population is finite. x1 is the first value drawn from the finite population of size n, and x2 is the second value drawn from the sample, etc. xn is the nth value drawn. Then the joint PDF f of x1, x2, etc. up to xn is equal to 1 by n into n minus 1, etc. up to n minus n plus 1. Then this constitute a random sample, because you may draw one particular value in the first time and some other value in the second time, no? So that will again constitute a random sample. So in this case, the marginal distribution is given by, marginal density is given by f of xr equal to 1 by n, where this xr denote the value c1, c2, etc. cn, and the mean and variance are given by this formula. That is, the population mean is summation ci by n, sigma square is summation ci minus mu the whole square into 1 by n, and the joint distribution is given by g of xr xs is equal to joint distribution of two variables is equal to 1 by n into n minus 1. Previously we have seen the joint distribution for n variables, isn't it? 1 by n into n minus 1, etc. n minus n plus 1. So here for only for two variables, xr xs is equal to 1 by n into n minus 1, right? Next one, covariance of xr xs. In the previous case, if xr xs are the rth and s random sample of random variables of a random sample of size n, then covariance between xr xs is equal to minus sigma square by n minus 1. This n denotes the sample size and sigma denotes the population variance. If x bar is the mean of the random sample of size n from a finite population of size capital N with mean mu and variance sigma square, then expectation of x bar equal to mu and variance of x bar is equal to sigma square by n into n minus n by n minus 1. So see the difference for population, for sample from a infinite population, expectation of x bar equal to mu. For infinite population, what did we study? Expectation of x bar equal to mu and variance of x bar equal to sigma square by n. But for finite population, sigma square by n into n minus n by n minus 1. So if the sample is taken from a finite population, there is a change in the variance. Okay. Next one, if again I am taking a finite population, independent random variables constitute a random sample of size n1 from an infinite population with mean mu1, and x21, x22, etc. constitute a random sample of size n2 from an infinite population with mean mu2, variance sigma 2 square, etc. Expectation of x1 bar minus x2 bar equal to mu1 minus mu2, and variance of x1 bar minus x2 bar equal to sigma 1 square by n1 plus sigma 2 square by n2. This is nothing but difference of mean. Okay, usually when we study about a mean and variance in statistics, no, we talk about difference of mean and difference of variance, no, difference of mean, no, not variance, only difference of mean. So here also from an infinite population we are taking two different samples, and x1 bar is the mean of the first sample and x2 bar is the mean of the second sample. Then expectation of difference of their means is equal to mu1 minus mu2. What is this mu1? Mu1 is the population, that is first population is there, no, that mean is mu1, and the second population mean is mu2, and variance of the difference between mean x1 bar minus x2 bar equal to sigma 1 square by n1 plus sigma 2 square by n2. The sigma 1 square is the first population's variance and this is second population's variance. Okay, next one, if x1, x2, etc. xn are independent random variables having identical Bernoulli distribution. So here we are taking, right, sample from a Bernoulli distribution with the parameters theta, then x bar is the proportion of success in n trials, then expectation of theta cap equal to theta and variance of theta cap equal to theta into 1 minus theta by n. So in case of Bernoulli distribution, expectation of theta cap is equal to, okay, what is this theta? Proportion of success theta, and variance of theta cap equal to theta into 1 minus theta by n. And similarly this is difference between means, where theta 1 is the from the sample, theta 1 is for the sample 1 and theta 2 is for the sample 2. What we have previously studied, no, the same thing for Bernoulli distribution. Expectation of theta 1 cap minus theta 2 cap equal to theta 1 minus theta 2, and variance of theta 1 cap minus theta 2 cap equal to theta 1 into 1 minus theta 1 by n1 plus theta 2 into 1 minus theta 2 by n2. Next, if a random sample of size n is selected from finite population that consists of integers 1 to etc. up to n, then expectation of x bar is equal to n plus 1 by 2 and variance of x bar equal to n plus 1 into n minus n by 12n. This is a particular case. So what do? We select integers 1 to n. So for that the expectation and variance are given here. Next one is chi-square distribution. Okay, when will we have this chi-square distribution? See, if x is a standard normal distribution, x has standard normal distribution, then x square has special gamma distribution and it is called chi-square distribution. Okay, now the PDF of chi-square distribution, suppose if x is a chi-square variate with new degrees of freedom, this new denotes number of degrees of freedom, then the PDF is given by x power nu minus 2 by 2 into e power minus x by 2 by 2 power nu by 2 into gamma of nu by 2 for x positive, otherwise it is 0. Right, so this is the PDF of chi-square distribution with new degrees of freedom, and the mean of chi-square distribution is nu and variance is 2 nu. What is this nu? Degrees of freedom. And the moment generating function is given by mx of t equal to 1 minus 2t power minus nu by 2. But in sampling distribution, when will we arrive at chi-square distribution? That is the question here. See, if x has standard normal distribution means what? Mean equal to 0 and variance equal to 1. In that case, x square of the random variable follows chi-square distribution with nu equal to 1 degree of freedom. Okay, so standard normal distribution, x is a standard normal distribution, then square of the random variable follows chi-square distribution with nu equal to 1 degree of freedom. Suppose I have n such independent random variables, each one is having standard normal distribution, that is each one is having mean 0 and variance 1. In that case, summation of xi square, okay, previously we talk about a single random variable and its square, no, now I am taking sum of squares of n random variables, then this follows chi-square distribution with new degrees of freedom. What is this nu? Nu is equal to, how many variables are here? N. So nu equal to n. Okay, next, if x1 x2 etc. up to xn are independent random variable having chi-square with nu 1 nu 2 etc. nu n degrees of freedom, then summation xi has chi-square distribution with nu 1 plus, that is here if each one is chi-square, then sum of all the chi-square random variates is again a chi-square variate with degrees of freedom equal to sum of the degrees of freedoms of the random variables. Okay, right. Next one, if x1 and x2 are independent random variables, x has a chi-square distribution with nu 1 degrees of freedom, x1 plus x2 has a chi-square distribution with nu degrees of freedom, then x2 also has chi-square distribution with nu minus nu degrees of freedom. This follows from the previous result. Okay, next one, where do we have this chi-square distribution? In sampling distribution. See, suppose x bar and s square are the mean and variance of a random sample of size n from a normal population. From where we have taken normal population. What are the population mean and standard deviation? Mu is the population mean and sigma is the population standard deviation. Then x bar and s square are independent and the random variable n minus 1 s square by sigma square follows chi-square distribution with n minus 1 degrees of freedom. Okay, so this is where we associate the chi-square distribution with with the sampling distribution. Okay, that is n minus 1 into s square by sigma square. This is going to be a random variable. Why it is a random variable? Because if you change the sample one by one, if you move on from one sample to the other sample, this s will be changing, isn't it? Right? Then this s will be changing, so this will form a group of random variables, so that will follow chi-square distribution with n minus 1 degrees of freedom. At probability of x greater than chi-square with alpha nu, what is this alpha? Level of significance is equal to alpha. Okay, this we use for finding the values of probability from the chi-square table. For doing problems we use, but in this video I am just stating only the important key points only. Right. Next one is t distribution. T distribution also we used to do many problems, but where do we use this t distribution? In sampling distribution. That is what we are going to see. Suppose y and z are independent random variables. Y has a chi-square distribution with new degrees of freedom and z has a standard normal distribution. Then t equal to z by square root of y by nu. Okay, this follows t distribution and its PDF is given by f of t equal to gamma of nu plus 1 by 2 by gamma of nu by 2 into root of pi nu 1 plus t square by nu power minus nu plus 1 by 2. So this follows, what is this random variable? Z by root of y by nu. This follows t distribution, and probability of t greater than t of alpha comma nu equal to alpha, and the table contain values for alpha greater than, alpha is what, level of significance greater than 0.5. Since it is symmetrical about 0, we have on both sides t 1 minus alpha comma nu is equal to minus t alpha comma nu, because it's a symmetrical one. When nu is 30 or more 30 or more, probabilities related to 30 or more probabilities related to t distribution are approximated with the use of normal distribution. See, t distribution is used for doing problems. We very well know this is used only for small samples, isn't it? When do we say whether it is a small sample or large sample? If the sample size is less than or equal to 30, it is said to be small sample, otherwise it is said to be large sample. Only for small sample we use t test. For more than 30, if the sample size goes more than 30, we used to have normal distribution. Okay, then if now we are going to associate the t distribution with our sampling distribution. See, x bar and s square are mean and variance of a random sample of size n from a normal population. So here also we are taking from a normal population, right, with mean mu and variance sigma square. Then t equal to x bar minus mu by s by root n follows t distribution with n minus 1 degrees of freedom. Let me compare the previous result and this result. So previously we have seen chi-square distribution. How do we associate with our sampling distribution? N minus 1 s square by sigma square follows chi-square distribution with n minus 1 degrees of freedom. All the previous assumptions are same, right? That is, the population follows normal distribution, then n minus 1 s square by sigma square follows chi-square distribution. Here x bar minus mu by s by root n, this follows t distribution with n minus 1 degrees of freedom. Okay, now these are the that is a possible level of significance for chi-square and t distribution. For that is, the level of significance are 19. Frequently we use only 99%, 95%, that is 99 means 1% level of 1%, this is 5%, isn't it? Like that we use. Now here it is 10%, 5%, right? And then here this is 1%, isn't it? 10%, 5% and 1% level of significance. These three values we frequently use for t table, right? So these are the possible level of significance. Next one is F distribution. If u and v are independent random variables having chi-square distribution with nu1 and nu2 degrees of freedom, then f equal to u by nu1 by v by nu2 is a random variable having f distribution, and its PDF is given by gamma of nu1 plus nu2 by 2 by gamma of nu1 by 2, gamma of nu2 by 2, gamma 1 by gamma 2 power nu1 by 2, f power nu1 by 2 minus 1, 1 plus nu1 by nu2 f power minus nu1 plus nu2 by 2 for f greater than 0, otherwise 0. Now for table values, probability of f greater than alpha nu1 comma nu2. Here in chi-square and t we have only one thing, that isn't it, nu1 for degrees of freedom. Here we have two values, nu1 and nu2, right? So f greater than f alpha nu1 nu2 is equal to alpha. So here we usually take 5% or 1% level of significance. Now, how we associate this with the sampling distribution? So here we need to take two random variables, no? So for that we take two samples, s1 square and s2 square are the variance of independent random samples of size n1 and n2 from normal population with variance sigma 1 square and sigma 2 square. Then f equal to s1 square by sigma 1 square by s2 square by sigma 2 square is a random variable having f distribution, and its degrees of freedom is what? N1. For f distribution you have to write 2 degrees of freedom, n1 minus 1 and n2 minus 1 degrees of freedom, right? Next one, if x is a random variable having chi-square distribution with nu degrees of freedom and nu is large, then the distribution x minus nu by root 2 nu can be approximated with standard normal distribution. Okay, x follows chi-square distribution, then x minus nu by root 2 nu follows what? Standard normal distribution, right? The another result is x follows chi-square distribution with nu degrees of freedom. Then for large nu, root 2x minus root 2 nu can be approximated to standard normal distribution. Next one is, if x follows f distribution with nu1 nu2 degrees of freedom, then y equal to nu1 x follows chi-square distribution. If t follows t distribution with nu degrees of freedom, then x equal to t square, that is square of the variable, follows f distribution with 1 comma nu degrees of freedom. And if x follows f distribution with nu1 nu2 degrees of freedom, then 1 by x follows f of nu2 comma nu1 degrees of freedom. And similarly, if y follows beta of nu1 by 2 comma nu2 by 2, then x equal to nu2 y by nu1 into 1 minus y follows f distribution with nu1 comma nu2 degrees of freedom. Okay, that's all for this video. So we have discussed all important key points for sampling distribution in this video. Thank you.